Hello, Robert Smith here from M2 Technologies, here to present Autodesk CFD. Let's cover some basics. What is simulation? Simulation is an integral part of the digital prototyping process. Essentially, the 3D CAD model of your product is your digital prototype, the sole source of truth from which information flows to design and engineering, test and validation, manufacturing and production, and sales and marketing. Simulation takes place in the test and validation phase of the digital prototyping process. This is the phase of your process where critical questions need to get answered. Questions like, will my part break? How light can I make it? What happens when the temperature changes? These questions have traditionally been answered by building a physical prototype for testing, a costly and time-consuming process. Leveraging your digital prototype and the Autodesk simulation software portfolio, products can be tested in a virtual environment, thereby reducing or eliminating costly physical prototype iterations. Why simulate? Simulation leads to better products in less time and at lower costs. Performance can be predicted, and materials and design features can be optimized. This leads to a higher quality product. Costs can be reduced as fewer physical prototypes are needed for testing, and defects that may lead to unsatisfied customers can be uncovered while corrective action is still relatively inexpensive. Finally, innovation is fostered. Designers and engineers are free to explore more what-if scenarios, as testing these ideas digitally is more feasible than manufacturing a prototype. One of those crazy ideas may be your next big innovation. What makes Autodesk Simulation different? Who uses Autodesk Simulation? Autodesk Simulation is built from the ground up to be fast and easy to use. Note the triangle graphic on screen. This triangle represents the entire community of engineers and designers. Traditionally, highly educated and highly specialized individuals, represented by the top portion of the triangle, have been relied upon to perform FEA analysis. These individuals are typically career analysts. They are expensive people who use expensive tools. This type of analysis is often done at the end of a design cycle for validation purposes. Autodesk Simulation is part of a newer approach to simulation called upfront simulation. It's for the everyday engineer or designer. These individuals often wear many hats, and running analysis software may only be a part-time role. They need results early in the design process to help them make more informed decisions while the product is still in development. For this reason, they need the tool to be easy to learn and easy to use. Autodesk Simulation serves these users. Let's compare the traditional design process with the digital prototyping design process. In the traditional design process, the initial concept is developed using a combination of past experience, hand calculations, and educated guesses. Using this method, it is not unusual for the first physical prototype of that design to fail. This results in the need for another iteration of the process, which means more design time and another physical prototype build. Each iteration of this loop adds cost to the process and increases the time it takes to get to manufacturing and to market. When a design does pass physical testing, there is little confidence that the design is optimized. It did not fail, but is it over-designed? In contrast, the digital prototyping method uses virtual testing to eliminate failed designs before a physical prototype is constructed. Initial concepts may fail to meet requirements, but iterating digitally is far less time-consuming and costly than iterating physically. In fact, iterating the design is so efficient with digital prototyping that the designer can afford to continue iterating even when the design has passed, in the search for a design that not only works, but is of the highest quality and lowest cost. New innovations can take shape, and better products are the result. All of this before the first physical prototype is constructed. What is CFD? CFD, or computational fluid dynamics, studies the flow of liquids and gases in and around solid objects. Thermal effects can also be modeled. Autodesk CFD models a wide array of physical effects. Standard offerings support steady-state laminar and turbulent incompressible flow, conduction, and forced or natural convection. Advanced CFD offerings support transient analysis, compressible flow, radiation, mixing, and more. With CFD motion, study how pumps, fans, blowers, valves, pistons, and other mechanical devices interact with and respond to fluid flow. Motion can be fluid-driven, where components are reacting to the flow, or mechanically driven, where components drive the flow. Direct data exchange with simulation mechanical allows for inter-product multi-physics simulation without the need to recreate inputs manually. Thermal and fluid pressure loads are easily transferred to simulation mechanical for stress analysis, saving setup time and allowing for more accurate product strength prediction. Autodesk Simulation Flex offerings deliver flexible cloud computing capabilities, as well as local machine solving. Flexible solving options enable you to simulate where and how you want, based on your needs. If you are setting up an analysis, use your local resources to iterate and optimize your inputs. When you are ready to kick off a longer, more computationally intensive simulation, use the power of the cloud and free up your local resources for other tasks. Now let's take a deeper dive into a full demonstration.
Welcome to this demonstration of Autodesk Simulation CFD. Here we're going to use this headlight assembly to introduce you to some of the powerful thermal management capabilities that are available to the analyst as well as the designer. Simulation CFD provides detailed material property information as well as robust calculations for producing accurate results. It's also intuitive enough for designers to gain information early in the design process for making changes when it's most affordable to do so. Autodesk Simulation CFD opens several native file formats, including Inventor, Pro-E, Creo, SolidWorks, CATIA, and NX. Any modifications to the geometry in the native CAD system are updated in the design scenario of choice for comparing the calculated results. We're going to analyze 3 different sets of lights in this fixture. There is the main HID xenon light, as well as the LED lighting above and below. Combination lights such as these create new challenges for OEMs and exterior automotive lighting suppliers. Our goal in this design is to preserve the clarity, brilliance, and life of the LEDs. In order to do this, we have to keep the LEDs within operating temperature and also minimize the temperature difference between each of them to avoid color shifting. As you can see, we have 4 different designs for virtual testing. We'll show the differences between them when we get to the decision center. Comparing the results between them will help us to answer key questions. Will heat sinks be needed? What are some ways to direct airflow due to buoyant forces? Should we add vents to the housing? And if so, where and how big do we make them? These questions can be accurately answered before a single physical prototype is made. The setup for each design is an intuitive process. In the Setup tab, we simply specify the material used for each component, key in the heat power for the bulb and LEDs, create the mesh, and finally solve. Beginning with the material, first you'll notice the air volume has automatically been generated, saving the time it would normally take to model it from scratch. Let's take a look at some of the material types for the solid components. As you would expect, there is an extensive library for common material options for plastics and metals. The property settings for each of them provides everything you need to gain accurate results. For example, the glass we're using is transparent. There are emissivity and transmissivity settings for its ability to absorb radiation or allow it to pass through to another object. Also take advantage of design components such as LEDs. There are several samples to choose from or create your own. Simply enter in the thermal resistance between the LED and the board and the case. You will see in a few minutes the solver produces thermal results for all 3 items for each LED. There are lots of items to choose from for material. There are PCBs, check valves, centrifugal pumps, thermoelectric components, heat exchangers, and heat sinks. Choose these items rather than modeling the detailed 3D features that take extra time to solve. Gain accurate results in a fraction of the time. Heat generation is then applied to each light. We'll use 20 watts for the HID bulb and this is acceptable since our goal isn't to analyze the bulb itself. Our main intention is to find out how the heat from the bulb is going to affect the rest of the headlight. Each one of the LEDs is set to half a watt. There is also the option to apply forced air to the outside of the headlight with a wind velocity. Even specify the temperature of the air for warm or cold weather conditions. That would be a good idea for a future analysis, but for our purposes we can solve more design scenarios faster by using a film coefficient, which emulates the outside temperature and wind. There is a mesh preview that helps to see the initial size of the elements before the study is run. Designers have several options for editing the mesh. For starters, choose the solid object and refine the number of elements. Use a region or 3D box that surrounds several components. The region is interactive on the graphics view, and the size of the elements can be dragged up and down as well. And finally, you should know that the mesh size can be set to change automatically based on high flow gradients. Accurate results can be gained with no manual effort to the user. Okay, now that the setup is finished, it's time to solve for all 4 of our headlight designs. The solver provides several options depending on the engineering goals. Run a steady state or transient analysis. Also use the option to run the calculation in the cloud. This is a great option because it frees up local computer resources for working on other tasks during work hours. All 4 of our designs are solved simultaneously in the cloud. For other preferences, here we're including convection and radiation as a means to cool the bulb in the HID light. There are also advanced calculations that can be added for humidity in case we decide to add vents to the headlight housing. And now for the best part. It's time to take a look at the results. Section planes are a great way to review the temperature and velocity of the air and the internal components. They are interactive, enabling the ability to translate and rotate to any location on the model, simply by dragging the triad on the plane. The heads-up user interface provides all the options needed to access the settings. Change the color plot to show temperature or velocity. There are many ways to view the results on the plane. The use of vectors is a great way to check the velocity profile for the direction of the flow, or check for any dead zones in the fluid volume. The actual values can be seen dynamically in the lower left-hand corner simply by hovering over the plot. We'll show several ways to gain the information you're looking for. Charts are a great way to review the results, and they are made simply by selecting points along a path. Here we can choose between velocity and temperature, among several other options depending on our needs. The summary checkbox will be used to compare the different designs in just a moment. We saw the flow trajectory on the plane using vectors. This can also be observed in 3D using traces. Traces not only display the direction of the flow, they can also contain mass for understanding the behavior of small objects contained in the fluid. This takes seconds to show the internal flow on any location of the design, as opposed to several days or weeks to make physical prototypes and prepare them for empirical results. Isosurfaces are very helpful to our design process to find out more about the heat coming from the HID bulb. This plot creates a 3D surface displaying the specified temperature. Let's take a look at 85 degrees Celsius. The surface color can display other results such as velocity. Even use the option to show vectors instead of the shaded surface. We can then see the direction of the flow on the isosurface. Now that we have seen the result types, let's use them to make a better design for the headlight. We have 4 different configurations that came from the CAD system. The first design is our baseline. The second design contains heat sinks for both sets of LEDs. The third and fourth design contain geometry changes for the depth of the rib on the inner shroud. This will hopefully direct some of the warm air from the bulb away from the LEDs. The decision center is a fantastic way to compare the results between each of the 4 design scenarios. Taking a closer look at the section plane, each design can be dragged into its own viewport. The orientation and legend remain in sync, and we can see here that design 4 is performing the best with a larger rib on the shroud. Let's also have a look at the isosurface. Once again, these results will show whether the rib is doing its job to direct the warm air away from the LEDs. We can see that Design 3 is doing a pretty good job. Design 4 is doing noticeably better. Now it's a good time to take a look at the temperatures of the LEDs. Here you can see the junction temperatures of all the LEDs in the upper set. They can be selected individually to check the temperature in each design. The entire list can also be saved as a CSV file to be opened in Excel. In here we can create our own charts for the temperatures of the LEDs for each design. We can see that the temperature of the fourth design not only has lower temperatures, the range in temperature is also what we're looking for to avoid color differences in LEDs. Remember the graph we showed earlier for the temperature and velocity. We can use that same plot to compare our 4 different designs. The velocity overall is higher in design 4, which is good, and the temperature in design 4 is low and consistent along the path compared to the others. Finally, we can generate a report that can be sent to customers and coworkers to review as a Word document or PDF. It is complete with a cover page, table of contents, material information, boundary conditions, mesh, and of course the results. Simulation CFD is part of the Autodesk digital prototyping strategy. It is a robust solution for creating the best design possible before any physical prototypes are manufactured.
Who is M2 Technologies? M2 Technologies is the leading manufacturing design solutions provider in the Northeast, providing services such as training, consulting, and project shadowing. We are a simulation-specialized Autodesk Gold partner, as well as an Autodesk authorized training center. We have a deep roster of talented technical specialists with expertise in design, data management, CAM, and simulation tools. We have several locations throughout the Northeast, but we provide services all across the USA. Thank you for your time today.